Okay, everybody. So we're going to continue with our kind of going through the free response from the last AP Chemistry exam and showing you the visible learning objectives that go into each question. But I just want to kind of review where we've gone. So we've done questions 1 through 3. So if you remember the way the free response is set up, is the first 3 questions are kind of the biggest questions. You spend the most time on those, about 20 minutes per question or so, because you can get 30 total points. They're 10 points apiece. And if we kind of scroll through, I've outlined the VLOs for each question, and you notice you have like 10, like 8 to 10 to 12 sometimes different visible learning objectives per question. So question 1, it was all these objectives. Question 2, we all through these. And again, notice how they kind of bounce around. Unit 2, Unit 1, Unit 3, Unit 5, all in question 1. Then when we get to question 2, Unit 2, Unit 1, Unit 6, Unit 3, Unit 4. And then when we get to question 3, Unit 1, lab, Unit 2, Unit 6, okay? And so look at, this list of VLOs for those questions. It's pretty long. But then when we go down to the next part of the test, the shorter questions, notice how question 4, boom, it's just 3. Question 5, just 3. Question 6, we got 4 or 5. Question 7, we got 4 or 5. So, they're kind of, these questions are only, again, worth 4 points apiece. So if we look at, question 4, we got 4A, B, and C. So that's 3 prompts. One of these is worth 2 points, because we can get 4 total points here, we can get 4 total points here, we can get 4 total points here. So you notice here we have 4 prompts, so each one of these is a prompt. And we'll talk more about this stuff during the year as we take our unit tests and as we start to prepare for the AP exam. You know, if you could look at question 6 and you see that there's 6A, 6BI, 6BII, and 6C. So there's four different prompts here. So each one is worth 1 point. So if there's a question, let's say in 6BII, let's say it asks you to answer a question and justify, you're only going to get 1 point for that, and you have to be right on both the correct answer and the correct explanation, right? So, and it's only worth 1 point. So, maybe the correct answer, but you're not sure exactly how to explain it or justify it. Then that would be a time where, well, I know if I don't justify it right, I'm not going to get the point. So I'm not going to waste my time trying to come up with some kind of explanation that I'm not sure is correct. And I'm going to go ahead and answer the rest of the questions that I'm sure I know how to do. And then if I do have time, I can come back and try to make up some kind of explanation. It would be something like here, like if we went to question 4, we only have 3 prompts, right? But we know we get 4 points. So one of these is going to be worth 2 points. But let's say question A asks you to justify and question B asks you to justify. Well, then you're not sure which one of those questions is going to be the 2.1. So that's when you definitely need to answer the question and then justify, because if it's a 2-point question, you'll get 1 point for the correct answer, then 1 point for the correct justification. So even if you have the incorrect justification, you still could get the 1 point for just saying it increases or it decreases or whatever the question is. So just kind of thinking about test taking skills, and I'll stop and I'll just get back to what we're trying to do is look at the visible learning objectives. So let's go back to the test itself. So notice when we get to question 4, it's just boom, 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 and that's it. It's this prompt, and this prompt, and that's it, and we're moving, okay? So they give us 2 different Lewis dot structures for 2 different compounds, 2 different molecules. Maybe they're going to ask about shape. Both molecules have the same shape, trigonal pyramidal. Maybe they're going to ask about bond angle. They would both be, you would say 107, or, you know, whenever you have 4 domains around the central atom, I always just say 109 because they allow you some leeway. They're both polar because they're both asymmetrical. If they're going to start talking about intermolecular forces, well, we know that since they're both polar, they both have dipole-dipole interactions. But because we have one of our Fon bonds here, we know this molecule is capable of hydrogen bonding, whereas this molecule is not. The other thing I would say about this is, yes, it's polar because there's asymmetry, but the electronegativity difference between nitrogen and chlorine is negligible. They both have basically the same electronegativity value. So you could make the argument that this bond is nonpolar because there is no electronegativity difference. And if you don't have polar bonds, even if you're kind of asymmetrical, you don't really have much polarity. So you don't need to memorize electronegativity values. You just need to know the trend. And you don't need to memorize that chlorine and nitrogen have the same electronegativity value. What you would have to recognize is based on the periodic trend for electronegativity is that chlorine and nitrogen wouldn't be that far apart. So even if there was a difference, it wouldn't be that big. So these bonds here would not be as polar as these bonds here. And therefore, if you don't have a big electronegativity difference, if you don't have very polar bonds, then even if you have a polar molecule that's not very polar in terms of electronegativity difference in the bonds, then the dipole-dipole interactions aren't going to be that strong, right? The more polar the bonds, if you have a polar molecule, the more polar the bonds, the stronger the dipole-dipole interactions between the particles, right? All right, but again, sorry, I'm getting ahead of myself. This is all stuff we'll learn throughout the year. Let's talk about the actual question in the visible learning objectives. So calculate the number of moles of NH2Cl, molar mass 51.48 grams per mole. So they're giving you the molar mass so you don't have to waste time calculating it yourself, but we should know how to do that. Present in 1 liter of a solution in which the concentration is 0.0016 grams per liter. Okay, so I was checking my visible learning document, and I don't really have one that's right on point, but this would just be a mole calculation. But this is when, notice that most of the time our unit of concentration is molarity, and they didn't give us, which is moles per liter, they didn't give us a concentration in molarity. They gave us in grams per liter. So this is going to be important where, wait a minute, AP Chemistry is a continuous course. It's a second course. It's course number 2. It's a second course of chemistry. And so the prerequisite is chemistry 1. So either regular chemistry or honors chemistry. And what do we do in regular chemistry and honors chemistry? A ton of dimensional analysis. So it's understood that you should understand dimensional analysis coming into the class. And it's not something that I put on the visible learning document. But really what you could do is say, hey, all the visible learning objectives from chemistry 1, I should know coming into AP Chemistry. Now, we're going to relearn a bunch of those things and we'll cover it. But, that is technically, it's second year chemistry course. So your first year chemistry course is stuff you already know, right? So anyway, and so this is when dimensional analysis comes into play. So when you have a unit grams per liter, you can say grams per liter, right? And so liters times grams per liter would cancel out liters and give me grams. And then again, if we go to 2-2, we got to be able to convert grams to moles. All right. So we use dimensional analysis to go from liters. So taking 1 liter of solution times the concentration that they give us in grams per liter will cancel out liters and give us grams, and then grams divided by the molar mass will give us moles. Okay, you don't have to put it in scientific notation. It's just when you have a number that small, it's probably easier. It's a time saver, but you could have easily said, .000031 if you wanted to. Yeah. Okay. So NH2Cl is highly soluble in water, whereas NCl3 is only nearly soluble, so somewhat soluble, as opposed to very soluble. Explain this observation in terms of types of relative strengths of intermolecular forces between each of the solutes in water. Okay. And I'm looking at my answer here. Okay, so I did mention water. I probably needed to mention more about water's attributes, but let's see. So I just kind of listed each compound's IMFs. So the NH2Cl is polar with a Fon bond, so it has all three: hydrogen bonding, dipole-dipole interactions, and London dispersion forces. LDFs, London dispersion forces. So let's go see what VLOs these are. All right, so this is 1-56. And so if we go to our visible learning document, 1-56. So again, I can predict if two substances are soluble using polarity of IMFs, and like dissolves like. All right, so the more alike intermolecular forces you have with water, the more water soluble you're going to be. All right. So what I probably should have done in my answer key here is have water listed well. So I would, in water, I would have these same three IMFs listed. So water, H2O, has hydrogen bonding, dipole-dipole, London dispersion. Whereas the NCl3 has dipole-dipole, and I might want to add weak dipole-dipole. I know I did it down here. And the reason we know it's weak is because the bonds aren't very polar. And the reason why we know the bonds aren't very polar is we know that there's not a big electronegativity difference between nitrogen and chlorine. Based on the trend, we know there's not that big of a difference, right? So, and because we don't have a Fon bond, H bonded to N, like we do over here, we don't have hydrogen bonding. We just have dipole-dipole interactions and London dispersion forces. So, so we have to explain it, not just list the IMFs. So NCl3 is only slightly polar and has weak dipole-dipole forces, whereas NH2Cl is more polar and has hydrogen bonding like water. So it interacts with water more than NCl3. There you go. All right, so I did mention that water has hydrogen bonding. I probably should have listed all three, I think, but this is most likely the 2-point question, because there's a lot of stuff. And again, I probably should have added water and said hydrogen bonding, dipole-dipole, and London dispersion forces for that too. All right, so let's move to part C. So part C, the value of the molar heat of vaporization for NCl3 is 32.9 kilojoules per mole, and calculate the amount of energy required to vaporize 15-gram sample of NCl3. And notice they give us the molar mass. That's very nice, so we don't have to sit there and calculate it. So this is just from unit 3 again. And it's 3-3, 7. And it's just, we've already had, in this test, we already had a calculation just like it. But it was using the molar heat of fusion. So, 7. I can calculate the energy required of a phase change. And so this is where we're using the delta H of vaporization, which they gave to us. All right, so we'll go to here and we'll take we'll take our 15.0 grams and convert it to moles. The reason I convert it to moles is because the unit for the heat of vaporization they gave me is energy per mole. And so then once I have moles, I'll multiply it by kilojoules per mole. That'll cancel out moles and give me my energy in kilojoules. So it would take 4.1 kilojoules to completely vaporize this many grams of NCl3. All right. All right, let's move on to question 5 here. Okay, so question 5, they give us this table. And, one thing to note up to this point is we didn't have any questions from Unit 7. There was we had no questions from Unit 7 yet. And if we look at the sheet I made, notice that question 5 is only from Unit 7. So 7 and it's all the same one, 7-2, 7-2, 7-2. So real quick, if we go to Unit 7 and we go to 7-2, You'll notice there's a lot of subcategories here. So it's 7-2, but there's 14 different objectives under 7-2. So it's no surprise that there's a lot of questions just from 7-2. All right, so let's go to the question itself. So they give us the rate equation for this reaction. So this is all stuff that we've never talked about: differential rate laws, integrated rate laws. This is nothing we've learned in Chemistry 1. We've talked about half-life before, but only in terms of nuclear decay. So I'm going to bring up the term half-life here. But it's not in terms of nuclear decay. It's in terms of just how long it takes for the amount of this reactant to cut in half. It's in terms of how fast the reaction goes. Okay. But they give us this. This is called the rate law. It's called a differential rate law for this reaction. And the thing to notice about that is there's a rate equation. You'll have rate equals K, and it'll be times the concentration of each reactant. Well, if you look at here, there's only one reactant. And what you'll do is you'll raise this to the power, so we can either raise it to the first power, which it is right now, so it's raised to the first power, that's why there's no one exponent. But it could also be raised to the second power. And it could also be raised to the 0 power, but if it was raised to the 0 power, it wouldn't be written here because anything raised to the 0 power is 1, right? So in a rate equation, the exponent here could be 0, 1, or 2, and it's 1, so that is telling us this is a first order reactant. Okay, another clue that this is first order is that if you notice, the amount of time it takes for the sample to cut in half remains constant. So notice that we went from 0.16 to 0.08, that's half, in 1.66 hours. But then to go from 0.08 to 0.04, which is half again, it took the same amount of time. It took another 1.66 hours. If we double this, we get 3.33, right? And then to go from 0.04 to 0.02, it took us the same amount of time again, 1.67 hours. So that's another clue that this is first order, even though they spelled it out for us here, first order. A characteristic of a first order reactant is that the half-life for it stays constant. So the amount of time it takes for the amount of it to cut in half always is the same amount of time, no matter how much you have. So in part A, determine the value of the rate constant K for this reaction. So this equation right here is on your formula sheet, and it's only used to if you have a first order reactant. Well, they told us it was first order, or we could see by the data it was first order. And so we know the half-life, the amount of time it takes for it to cut in half is 1.67 hours. So we plugged in 1.67 hours into the half-life. This is a constant that's on the formula sheet, and all we have to do is solve for K. So we plug in, we had to recognize that that's the half-life. We plug it in, we solve for K, and the units for K are, for a first order reaction, is always 1 over the amount of time. So the amount of time here was measured in hours, so it's 1 over hours. And another way to write 1 over hours is hours to the negative 1. Okay, so let's see where that is in the VLOs. So this is 7-28. So let's see what 7-28 says. I can solve for the rate constant K and determine the proper units. Okay. So let's go to the next question. So they give us a reaction mechanism, and they want us to identify which step of the proposed mechanism, 1, 2, or 3, is the rate determining step. Justify your answer in terms of the rate law given. And this is VLO 7-210. If we go to number 10 here, I can use a mechanism to determine the rate determining step. And kind of what we're doing here is using the rate law to determine the rate determining step of a mechanism, so it's a little bit different. But the answer is step 1, or you could say step 2. But step 1, it has to be step 1, and it's because it shows N2O5 as a first order reactant. And that is in agreement with the fact that we knew it was first order. Okay? But again, that's not anything that you need to know right now. This is the stuff we're going to talk at the end of the year, right before the exam. Unit 7 is our last unit, and so we will get there, and you will understand this. Okay. And then part C, if this experiment was repeated at the same temperature, but with twice the initial concentration of N2O5, would the value of K increase, decrease, or remain the same? Okay, so if they had, instead of asking about K, if they had asked about the rate, because it was first order, if you double the concentration of a first order reactant, the rate doubles. But they're not asking about the rate, they're asking about K, which is the rate law constant. And the key word there is constant. Constants in chemistry stay constant as long as the temperature doesn't change. So because the temperature stayed the same, we know K has to stay the same. So K would be the same, it only changes if temperature changes. And that is 7-214. If we look at that, I understand that the rate constant K remains constant unless temperatures change. There you go, boom. All right, perfect. All right, let's keep rolling to number 6 here. Okay. Number 6, they give us this thing, absorbance versus wavelength. A student wants to determine, and real quick, I just want you to see number 6. Number 6 is all lab stuff. Now, if you go to 6BII, that is lab stuff or 2-2-7, but it's basically all lab technique stuff. And it's basically L-1, which is, if we go to the lab stuff, which is right now, it's colorimetry, not calorimetry, colorimetry in Beer's law. All right. So if we look at the question, it says, to determine the optimum wavelength for an experiment that measures the concentration of permanganate, the student takes a sample of a solution and measures the amount of light absorbed by the sample over a range of wavelengths. So they shot this wavelength through the light and see if light was absorbed, this wavelength, how much light was absorbed, all the way through. Okay, and then they charted it. Identify the ultimate wavelength that the student should use for the experimental procedure. So absorbance and concentration we're going to find is directly proportional. We'll learn about this throughout the year. And the optimum wavelength is the one where you get the most absorbance. So you're going to find the highest absorbance. So basically anywhere between 500 and I would say 575 would be fine. But if you can pick any wavelength, you would pick the highest one, and that's right in the middle here at 525. Okay? But they would probably, 525 is what most people who understand chemistry would probably say. So the good chemistry students, most of them in the country probably said 525, but they would probably accept a range probably between maybe not 500, but maybe 512 to 555 or something like that. They would accept a range, but 525, boom. All right. And that's going to be our Beer's Law lab, so we'll learn about that. All right. The student uses a stock solution with this molarity, 2.4 times 10 to the 3 potassium permanganate, to prepare the standardized solutions of permanganate that are needed to construct the calibration curve. Right? The student uses a 100 milliliter graduated cylinder to measure a certain volume of potassium permanganate stock solution, as shown in the diagram. So here's the graduated cylinder, and here's the measurement. What is the volume the student should record? So if we go to our visible learning objectives, this is BI, and it's L-8, and L-8 is all about measurement. So it's being able to take a proper measurement and knowing that you have an estimated digit when you're using things that have graduations, things that have calibrations. So not a digital instrument, but things that you're reading off the tick marks, you're reading off the graduations. You have to take one estimated digit. So the way we do that is if we look at this it looks like the meniscus is right at 92, right? So each of the graduations go up by 1 milliliter, right? Here's 90 milliliters, here's 100, and it would be 91, 92, 93, 94, 95, 96, and so on. So the calibration marks give me the ones place. So you are allowed and have to estimate to the tens place, but you can't go beyond the tens place. You can't go to the hundreds place. You're allowed one estimated digit. So if I know the ones, I can estimate to the tenths. So if you think it's 92 right there, right on the money, then you have to say 92.0. If you just wrote 92 milliliters, you won't get credit for that. Okay. Now, if somebody put 91.9, that would be perfectly fine. 92.1, that would be perfectly fine. The estimated digit doesn't have to be the same. That's why it's called an estimated digit. My estimate and your estimate might be slightly different, but you have to have that tens place there or you don't get the credit. All right. So calculate the volume in milliliters of 2.4 times 10 to the negative 3 molar potassium permanganate that is required to produce 100 milliliters of a standardized solution. So this is using our dilution equation. And if you look at our visible learning objectives, it's how to make a standardized solution. So that's why on this sheet here, I said it's L-5, but it's also understanding the dilution process, which is 2-27. So let's go up to 2-27. Oops. And it's, I understand the process by dilution and know how to use the dilution equation. There we go. All right, so we'd have to understand that this is M1 and this is V2. This is our final volume, and this is M2. So what we're really solving for is V1 here. So we plug that in here, we plug that number in here, we plug 100 in there, and we're solving for V2. So if we take 70 milliliters of this solution and we add distilled water to it so that it reaches a volume of 100 milliliters, now our new molarity is going to be 1.68. Okay, so that's what we did there. So dilution. And then if we go to the next one, they're basically asking the question. I'm not going to sit here and read it. You have a copy on the Schoology thing, so you can read it, or you can read it on this video, pause the video. But essentially, this is the process that the student was following to make this graph, absorbance versus concentration. And notice as absorbance increases, concentration increases, absorbance and concentration are directly proportional. Okay. And they want to know what could be an error that caused this data point not to be in line with the rest. So why was there a lower absorbance value here than what it should have been? So at this concentration, if we're following the trend, this concentration should have an absorbance value here, but it ended up with an absorbance value here. So what caused this absorbance value to be lower? And it would be because the solution you were testing was more dilute, less concentrated than what it was actually you thought it was. So if you notice, step 3 says rinse the cuvette with the standard solution. So first you rinse the glassware you're using. First you rinse with water, distilled water. But before you use it to measure something else of an actual solution, you're supposed to rinse it with that solution. Because if you have water droplets in there, when you add your solution to it, you're going to dilute it a little bit. So you always want to do a final rinse with the standard solution before you fill it up with the standard solution to take a measurement of. So most likely the student did not rinse the cuvette with the standard solution, so it was diluted by a few drops of distilled water in the cuvette and that should say from step 2. So this distilled water from step 2 diluted the solution because they forgot to do an initial rinse with the standard solution. And that would dilute the solution a little bit under, 0.12 or 0.0012, whatever that is there. And since it's slightly under, it didn't absorb as much as it should have because it wasn't this high of a concentration. It was probably more like this. So just those couple drops diluted it enough to bring the mark down a little bit. All right? All right. So I'll stop there with this video, and I'm going to come right back with question 7 and kind of a wrap up. All right? So...